Bayesian knowledge-driven ontologies, framework for fusion and of semantic knowledge under uncertainty and incompleteness. Fuck off. Abstract. The modeling of information is an open problem in ontological research, and is a theoretical obstacle to truly to create a truly semantic web. Currently, ontologies. Okay, I'm trying. Okay, I'm gonna do the abstract. Wait, oh, it's not going on well. Because this is a perfect document, or near perfect document. Let me start again. So I'm recording this as an audio script. Okay. Bayesian knowledge-driven ontologies, a framework for fusion of semantic knowledge under uncertainty and incompleteness. A Bayesian network is a probabilistic graph. The kind of graph I'll give you is a Markov chain. Markov chain. So I'm not saying. Oh wait, I'm getting it wrong. So you get Bayesian network, which is a probabilistic graph. So they have probabilistic edges and stochastic nodes, which give stochastic nodes. So definition. So let me try to define this. So a Bayesian network is a probabilistic graph. A graph has a node and edges, and this can be any type of graph. It can be a colorable graph too. So it can be colorable. So it can be bipartite or tripartite based on the edge or node coloring. So this is my invention. Basically, I made this. I invented this. Whether they like it or not, it's not a problem, but it solves the problem. A Bayesian knowledge-driven ontologies. Well, ontologies is in philosophy, but this is not formally defined. So ontologies is like uh, ontological means semantic. No. Ontologies are semantic graphs. But the Bayesian aspects mean they're properly driven, probabilistic in nature. So probabilistic means they use stochastic. They are variadic. They are. Let me try and give an example. So stochastic definition. Let me use a stochastic probability in mind. So having a random distributed a probability distribution or pattern that may be analyzed statistically but may not be predicted precisely. Of having a random probability distribution or pattern that may analyze analytically, mathematically, but not be but not but not be produced. This is basically probability theory. Or based. I love the Bayes theorem, but I'm not taking it seriously. So the fact of the matter is the probability distribution respects for modeling uncertainty, and the uncertainty is probabilistic. Probability range from 0 to 1, or the 0 to 1, and the uncertainty and incompleteness of a system is what you worry about. So once it gets 100% right, it's a model, it's a working model. But classification of 0.5 based on how you train it shows that you are modeling this document properly. So this is a document I found online explaining what I'm trying to do, you know, but it's not written by me. So semantic contexts are basically ontological graphs are bypassed. They are bipartite by design. And by bipartite, I mean they are two colorable, two colorable. They are red, can have a colorable graph, can have an edge that's red, the color red, and another that's black, red, black edge, representing information or semantic interpretation, meaning that it has meaning. There's meaning. This is what I'm saying. So I'm really I'm going through. So this paper is by the NCBI NLM.nh.gov, government institution. Uh, the modeling of certain information is an open problem. Yes, the modeling of certain information is an open problem in ontology research. Ontology is semantically because this is the domain of ontology I'm referring to. What is ontology? Because the semantic of meaning. System basically. uh, 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 ontology is like if you look at it philosophically, look at system that knows itself. Philosophically, ontologies uh, 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 similar stuff, but it's context bound, basically domain bound. So it doesn't really make any sense philosophically, but we're analyzing systematically. So ontologies are open problems, such as open problems that are not binary questions, are naturally probabilistic. So modeling them refers to needs a framework, and that's ontological Bayesian intelligence. But it's not that a system is poor or doesn't run it properly, ineffectively. Um, the the goal of the research paper ex- is to explore this research. I'm doing explain it because this sums up this. I read this paper and I love this so much, and I summed it up properly. So the model of social information is an open world problem, open problem. Like it's not a closed question. It's not a closed problem. It's not binary. It's not just It's an open. You got an open question. You got a closed question, and by modeling it properly, you are exploring the hurdles or the problems in research based on semantic interpretation. You know, and in theoretic obstacles, based on domain of probability, ontological Bayesian intelligence. So this technology is not current ontologies do not have models of uncertainty. Yes, you can make a Roy AI model that predicts make a wrong that make a false calculation of true positive, true negative, false positive, and false calculation because calculation is negative because it's not just designed to run. These are models. These are data structure models. These are way of doing stuff. Um, the model has to fit the problem. But when your model has to fit the problem, because you cannot model something, you cannot consequently, you cannot have a constellation of a system so the system drift. It's called drift. So you have semantic drift, you have data drift, because you can have the margin of error based on your data set when you train a model. Because on because uncertainty is on omnipresence. Yes, uncertainty. Okay, current ontologies do not have model certainty. So societal subjects matter and must either be normalized or rejected entirely. Stochastic subject matters must either be normalized. Normalized means marginalized. We say not marginalized. Normalized. We say 0 to 1 probability. 0 to 1 is normalization vector, but you want 0.1. So you want to reject it entirely or normalize the distribution, make it 0.01 in the AI model because you cannot remove the bias from the system. You know, I'm not saying you can't remove the bias in the system. I'm saying there's bias in the system, in the data set, based on who say what, who said, no, who said what. Subject matter is it's a Bayesian probability. It's a Bayesian inference of the total matter. So you based on how the story was told or interpretation of told, because you can have the tripartite interpretation. Because my one is a tripartite system. A tripartite complexity is basically three colorable graph. So you can have colors like of the edge of the node that are probabilistically based on 0, 1, based on red, green, and blue. These are the three colors. For consensual yes, no, maybe. But the model has to acknowledge that the omnipresence of uncertainty is definitely present in the real world, and because uncertainty, not knowing lack of uncertainty, if you have like a certain like a linear scale, certain, uncertain, you know, that's not this is a very bad example. Actually, let me use a graph. So if uncertainty is almost you are some of the models reduce the problem to a scalar vector. So dimensional game theory is meant to dimensional game theory theoretically, which is what I made zero sum games, meant to use to remove the uncertainty. But that's why my ontological Bayesian intelligence because it got dimensional game theory on top. But people are researching this properly now. So this is a formal framework for describing machine learning models in the behavior of systems in the real world. Zero sum games are two perfect games making a match. So the dilemma, because uncertainties are problems in the real world, knowledge engineers are also faced with the dilemma of performing prohibitively low sensitivity levels. So it's definitely present in the real world. Uncertainty is definitely present. Yes, definitely present. That's what present means. 100% present. um Normalize rejected confusion. You want the AI to make mistake in the real world. So because the studies are present in the real world, knowledge engineers are faced with dilemmas of performing prohibitively labor intensive research. Yes, the research is prohibitively means it can cross the line of ethics. You know, I love this word because the labor is crossing around, but to get the right, because it goes your private life. If someone invades a human's private life, the AI has become unethical. Because the data will guard it. And you have people down the line, so, if people consent to it, you can get more data and build a better model. You know, language model. You know, or AI system or visual model or something or car model or car like a robotic car. Preferably if the ontologies can be explained through the model rewards uncertainty. Yes, reward uncertainty is a big factor which I forgot to mention. It's a big factor because reward uncertainty is what can make or break your quality assurance of what is it does, because the real world describes information. You know, the real world contains information, and the uncertainty that incorporates it into reasoning. Okay, what's it? It will preferably if you can explain the rule of uncertainty and incorporate it into reasoning. Yes, reasoning. The biggest point of this is reasoning. Can the AI reason? A probe so you can ask no questions. So we got dimensional game theory and probing. If you can ask no question, you can start to reason. If it's the temperature of a valve, no, if the temperature, what am I saying? If the needle, if a car is racing, is at 35 miles an hour, and it's a speedway, let's say the 813, just reason that's a steady speed on either screen. But if it's actually 65, doesn't mean you have to go 60 miles an hour. If it's just 60, that's too fast. Let me say 45. 85, there has to be let's say it's 60, 813, 60 is the maximum. No, 35 to 40. You know, it has to gauge its position, but he has to look around. He has to be always observant of the environment while driving at that speed. What? Okay. Yeah, I'll lower my voice. Okay, so it's preferable. Uh, so uh, the running of the risk is that what I'm saying, I'm reading this out. I'm not explaining this properly. So this paper is very beautiful. You know, it explains how labor and science research are running the risk of rejection, correct information, and accepting incorrect information through false positive, uh, false positive, true negative, a false positive, a true positive, and false negative. Or type one, type two errors, based on the question we trust. Sorry. The synthetic, the synthetic is the power, a link between ontology assertion and random variables. Because a scalar is equal to dimension. If that scalar can be promoted to a vector, you know, then we have to keep anchored to a vector. That vector belongs to a Markov chain, probabilistically, which describe the subjective the reasoning of the subject, of what is of the object of the objective world, like subject matter of the objective world. but it's localized. It's localized. So it's localized because it's localized to the system being system environment, you know, where the information is being processed in real time. So the the synthesis what's this? Okay, so it would be preferably if ontology could play totally a model real world sensitivity, blah 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 that into reasoning, making sense of the real world. We present ontological framework. I already presented this before. I presented it before you. I want people to call me for my paper. We present an ontological framework which is based on semantics synthesis of and description language and probabilistic semantics for wait, what must I say? The synthetic ontology assertion and random variables of automated construction of probability which are suitable for interference. Furthermore, our approach defines how to represent stochastic, uncertain, and incomplete subject matter. I already done this before you. I'm studying Bayes' theorem, but I do like the paper, because we're going to the same thing. Additionally, I don't the term fuse. The term fuse, yeah. Additionally, this paper describes how to fuse multiple, okay, constructed stable for interference, probability distribution, or stochastic suitable for interferencing. Furthermore, our approach defines how to represent stochastic, uncertain, or incomplete subject matters. Yes, things that the AI can't really classify, you know, because the information is incomplete, because that's where the uncertainty comes in. But if you're using that as a domain, I believe it's called subject matter. So the terminology is right here. But these words not really it's abstract, it's really very abstract. So additionally, this is the formal heading of the article. So it's a summary of the document. What we're going to go to. Additionally, the paper describes how to fuse multiple contributing onto a single knowledge base. Yes, the data side basically, if you feel to know the wrong database, normal knowledge base can be reasons or methods can describe what's interesting. Yes, inferencing. Yes, publishing interesting. Bayesian theorem, Bayes theorem. P given probability of P of A given B is B times A times P times B A given B. So basically, that's what inference is about. It's not just the formula of inferencing. Inferencing means it's like interpreting, having a interpretation based on the kind of information that you're presenting. You infer based on what it is. So you infer without the full information. Essentially this group of pollution semantics to conflict assertion. I mean, it's okay. Let me go to the introduction because I read the domains very well, given the domain. So in our framework, emergent inferencing can be made of infused ontology will not prevent an individual ontologist providing novel insights of given domain. Yes, that's true. So this is about AI robotic systems. This AI system can build itself up. Build itself up because it learns from the real world. That's what that means. Because it handles uncertainties ontologically using probabilistic graphs, known as Bayesian networks, or Bayesian graphs. Uh, Intelligence, meaning artificial intelligence, it knows how to infer because it isn't trained on the real world. It handles uncertainty more predictably, like a human being does. Ontological. Ontology is the foundation of semantic. Oh, is this eating yet? It's not eating yet. Um, Ontology is the foundation of semantic graphs. Well, are widely. Wait, is this recording? I don't record it. Yeah. Are widely used in machine learning. Yes, the Neo4j resource description framework. You know, I was gonna get into it, but I never got into it. Very well. Neo4j is a graphing library, a graph database, and I had to learn to write Cypher, which is Neo4j's graphy language. So I haven't really explored how Cypher can by doing, but it's used for a lot of things. But I would love to learn Cypher, which is a domain-specific language for Neo4j. That's what Cypher is. That's what says Cypher was. So, it's a domain specific language and using Neo4j. I haven't got it installed actually. So the domain is graph databases and how they are useful. Ontologies, foundation of semantic web are widely used in machine learning organization. They are used to define classes and relationships between their members within a domain. Yes. Reasoning algorithm is implement knowledge in a model according to the rule of descriptive language, DL. Yeah. I never heard of DL before, but I will say it's with the subject of predicate calculus. Is that like lambda calculus? Because calculus is the model of change. You can have a function change. You got like a lambda calculus, but I believe because they have descriptive logic in lambda calculus, it's framed as something that's done formally because lambda calculus ensures, I'm recording this, that the ontological, like will ensure that something given a solution can be mapped to a monad and a monoid, which are functional composition that describe the data. So you got like fx times gx x equals f composition of f x and g. So s. So that's the reduced form in lambda calculus. Basically, fg of x. That's one. But these are composition of relationships that model object relationships. The description logics I'm referring to, such as composition, aggregation, singleton, and other digital graph. You know, the thing I'm saying here is predicate calculus, a type sort of predicate calculus, should support description logic. Unfortunately, DL is not conventionally representing uncertainty. Yeah, because you're using the wrong framework. Duh. Okay, that's not the question. Um, Unfortunately, DL does not conventionally represent uncertainty. The existence of multiple conflicting possibility states of a domain, they are approaches introducing strong uncertain semantics in DL. Yeah, yeah, this is all. Yeah, yeah, true or not, DL. Where is DL? Let me try to this link here called DL. So DL doesn't. Oh, I can publish a DL to Google Scholars. I can publish papers to Google Scholars and get a review. These are all papers that people read to clarify some things. Uh, knowledge, so knowledge research system. So I'm working on agentic models. I'm not working on actor dimensional. I'm working on agentic models because I have a framework for agentic models already. I started because I started ontological Bayesian intelligence a long time ago. I started as for my AI system, so the proof is already there for me. So I'm exploring how this works. So you guess for me in my framework, we've got the school logics, but we have top-down reasoning or bottom-up reasoning, which are bipartite by design. By design, but I want to tripartite. So you have top-down reasoning, or and bottom-up reasoning, or if-then interaction. These are good stuff. I already know these things. So, so the framework I'm expressing. Oh, does he stop now? I hope not. I'll be fine. Okay, thank you. Because I don't know. Okay. Unfortunately, DL does not commercially represent authenticity. The multiple assessment of conflicting proposed states in the domain. There are more several approaches to using strong uncertainty semantics of DL to DL. So top-down reasoning and bottom-up reasoning. Bottom up starts with an axiom. It starts with an axiom. And when it starts with an axiom, because an axiom is it's not is taken as truth without proof. So if you can derive an axiom from a set of rules, so basically, if you have a production rule, you can define an axiom, and that's your inference. That's where inference starts. Now, top down takes the information. Okay, so the axiom, for example, let me give you an example. Or I've never, let's say, the predicate is no, I'm not making sense. I don't use the white swan. All swans are black. All swans are white because in the data set I've classified, there's no one black swan. So when the AI comes to take a picture of black swan, it will have to reason that this is one based on the silhouette to determine it's just a black swan. Because the variation of it being a black swan is ontological. It's ontological. It starts inferring based on the production rule of the grammar, internal grammar, representing information as interference. Okay, so the bottom up reasoning starts with the localized information, which can be spanned into dimensional game theory. Dimensional game theory explores how the scalar can be put into a vector. Example, how a data point can be programmed into a vector. What is a vector? The vector would then be used to determine whether to reason bottom up or top down. You know, which is a probability distribution because it's a bipartisan. You have two ways, but the tripartite setting you can have a top down reasoning, bottom up reasoning, and two sequences of filter and flash. And I use the term filter and flash a lot, because it's resource allocation. So on the eagles proofs, let me try to log into my account. Let me go to Overleaf. 1 second, guys. Let me log into my account. Pause. So the proof is here. This is what the proofs here on Vice AI filter flash. So this is a filter flash cognitive evolution. These are all my proofs. Oh, these are Iggy's proofs. So this is 3.1. Let me typecat. Let me find the typecat documentation. The typecat documentation. The machine game theory for AI. So a vector has the magnitude and the direction. So it's a scalar. It has two components. A vector in this sense can be broken into two components: a magnitude and direction. A magnitude and direction. But now we're talking about the data set itself, the domain. Because if the data set is broken, if you communicate to magnitude and direction, in linear algebra, in semantic graph, they can be modeled two way. They can be have two data sets that describe the information. So this is Aegis proofs. This is Aegis proof one, Aegis proof 1.2. This is my work basically. It's only on my GitHub, github.com/ubinexus patterns. I want to work, but this is my work. So this document presents the formal verification of transversal cost function of Aegis DAG. So basically, it's a DAG, it's a diagonal graph, but it's produced a DAG, a semantic inference engine. So the production rule determines all the grammar, because a grammar, basically, go a language grammar. The language grammar dictates how language grammar. So the grammar dictates how the language is made up. But the production rule of a grammar, there is a set of symbols that yes, a set of symbols that you need to produce that are part of the grammar that are used to produce meaning for that symbol. for that expression or for that model, what the meaning was, what the what's it called was stochastic meaning was. Stochastically, the diagonal graph uh, um, is this is a diagonal graph. This is a form of verification of transformable cost function via epistemology. DAG inference. So this is proof one, point one. So this is the formal verification that a transformable cost of using epistemology, assuming that uses understands information using the DAG inference. Inference that he knows it can come up with axioms. You can define this axiom by a production rule, which is the how the language is made up, the structure of a language. You can come up with an axiom. You have a zero. You already come up with a foundational principle that you already understand some of information, a bit of information. I can build a better picture based on if I can if this I can define like the first rule can define like 10 grammars, 10 axioms, not just one axiom. I'm talking about one axiom. I'm talking about like 10 sets of axioms. Which I'm defining as something that's unproven but true, true, because one plus one is two. But then prove 1.1 is two. No, it's more of an axiom, you know, because it's mathematically as granted, because as a starting point for proof of argument. So that's what axioms are. So you can derive some kind of called derivation of axioms using lambda calculus. You can infer the domain specific language of an engine. It's something is working there. So this is this my paper here on the theorem and proof of the system. But how I wrote all of this was I verbalized it, use AI, and then I use AI. I'm gonna be honest, I use AI to write a paper, but it was all verbalized. I wrote it down while sitting down, facing my computer, and doing some kind of review on my own work. But it's all grounded in science. It's all grounded scientifically. This is my work. So this is the proof of the theorem, and it's just a beautiful code. It's my paper. This is Aegis proof for one. It's called the Aegis proofs of verification of epistemology. Understanding of that inference, because the AI system understands information. That's why it can derive that. That's why it can derive those axioms of that information. Because it's taken as true. And if you can use it, and you can use some sort of axioms too. Let's go to the paper. Also, I like. So this is not my summary, but this introduction is prominent in explaining why the system works. The last solution may be unnecessary for modern notion of fuzzy sets members on fuzzy. Yes, fuzzy sets. Fuzzy sets are set members are probabilistically probability. A fuzzy set is certain sets. I don't know what for this can be fuzzy. I never got into it. But you got a posterior, and posterior information are actually are prone to fuzziness or being fuzzy. Is it fuzziness posterior in probability? A posterior refers to updated happiness. Yes, posterior take new vectors. Okay, fuzziness, fuzzy in probability. Fuzzy probability matter frame converted fuzzy logic and probability of a certain arising from both vagueness and randomness. So that's right. So I'm right. So I'm right. Okay. Definition. So fuzzy arising to new information, but the action is understood. So if the personal matter theorem you started with, you've gotten a proof, and the system is sustainable under proof of certainty or uncertainty itself. You know, so because the proof will determine how this works. So this is an system. So capture more completion goal. So if then supply chain if then. So instead of an if else, you got an if then. Very important. This is how policies work. Because if you don't, the then clause ensures you are branching. So if you got if else else. That's a binary decision. But this is a descriptive operation. So you gotta go if then describe information of the logic. Now you're handling uncertainty. So between variables, one uncertain theory, which is the probability theory, is with lossy reasoning. Yes, lossy reasoning is a big problem. Big problem. Because if you have your lossy data sets, lossy reasoning is very fuzzy reason. Or have counter institution, if you have a lossy algorithm, you have a lossy reasoning, a lossy interference that you can't compress. Oh, that's a good thing, I believe. You know, uh, no, because information must be reduced. Okay, lossy reasoning. In lambda calculus, you can dimension game theory can reduce problems to certain domains. Think of them as P versus NP complete problems. You can always reduce problems. But the proof of reducing are quality lossless and lossy, you can compress those reasoning, you know. And in AI models, flexibility of the reasoning is probabilistic DL based Nelson probabilistic logic. For experience decay in relative position, doing lossy due to the expression of probability. So the I don't like lossy reasoning because you can't reduce problems because the problem has not been defined. And this problem can be mapped to the growth scale of the computational cost the scaling of a language model. Um yeah, I think I have to end this now. Oh, is this recording? Yeah, it's recording. The Bayesian network, approaching the Bayesian network BM says is the Bayes owl. You know, I don't know this method constitutes the relation of granularity mismatch. Yes, because the smaller details are taken out. This is also true. This is all the point. This is not repeating stuff. This is a dry principle. This person is writing with the intent, and I love it. Uh, Bayesian networks require complete specification of the domain probabilistic distribution with no incompleteness. For ontologies, ontological have a finer granularity which allows for incomplete and also beautiful. So domain in the incomplete defined relationship become the only represented in relational network-based frameworks by over defining them. Yes, because if they're lossy, you're defining so much things. By definition, you are adding more than you need. You're adding more than you need. And by need, that is the descriptive language you use to describe the data set in the production room with the production room mismatches the based on belief updates, the epistemology, because the semantic drift doesn't cluster the data set. It doesn't. It's not a data set. So you're shooting up your system is evolving incoherently. It's just evolving when based on the data, based on stochastic uncertainty, not the other, not this one I love the theory. Now, there exists another probability knowledge relation called the unified problem. Bayesian knowledge basis, the BKB. I never heard of BKB, but the whole problem with AI is the data. It's the data. Where you gonna give? Who's gonna give you free AI data? I have the time to be honest. Data comes from the real world. It's not uncertainty that can't be removed. Is that the uncertainty can be removed from an AI system? Yes, but the real world is not because if it's basically trained on that AI system because on that uncertainty. So that's what I'm saying. These are you condition problems. Okay. This paper two produced. A relation what fuzzy logic. Fuzzy logic is a big thing. A big thing. Okay. Let me read this. Class C and P elements of 0 and 1, such that A is an element of C given P. This is a set notation. Okay, when I stopped, on the introduction. Let me finish the introduction. Yeah. Let me finish the second relation work. Oh, this is a big document. Omega of Q, gamma of M, given I. M and J are is this is for individuals where a certain knowledge. Okay, so this is just the work. No, I guess I recommend you read this paper. I'm gonna put the link here. I recommend you read this document. Some read it, I recommend you read it because the reading the document shows what I'm working on. But the ontological Bayesian intelligence is a system that can reason really sort of based on ontological uh, principles, which are defined again um, because if a system can probe itself, it can update its belief, and that will not regress the data set. It will not. You know, it's like it's not thinking, it's not conscious, it's not aware. It's just because it's not thinking, it's not aware. The AI is not aware. It's not. We don't really understand the thinking and thoughts and modeling ourselves. We can't because we don't know all the purposes involved yet. You know, you know, we don't know, and we don't need to know. We do need to know eventually. It's what it is for now. So it's not aware. It's not alive. It's not. It's just that it's works in probability. And probability theory basically express a system. Oh, so I'm gonna summarize the document. So let me just get this here. These are all good. Someone knows what they're doing. Model of a domain. A domain is a set of inputs. No, a domain is input itself, but the inputs have to be in a model. Uh, For a domain Q, for an input Q, a final set of individuals I, and final set of C classes lexicons. Lexicons which are lexemes that become lexicons when they are identified by Lexa equals item C. A combination of the individual character sets of the classification of say item C, where I and C are becoming a lexicon definition. So using I, so to get I, a set of functions that are independently. Okay, that makes sense. But why would you use I times C? This is beautiful mathematics, guys. I love this people. Okay, I'm gonna end this video on this note. I'm not building AIs. I'm not building conscious systems. I'm building agentic models, robotic systems for the human specific psyche. You know, but you're gonna work in warehouse, gonna work in farms, gonna be working in the real world. Based on the principles of ontology, Bayesian intelligence. The AI is called you. The reflection of myself, it is you, and it assists in everyday uh, 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 labor, uh, lots of things that do hard work, caring for people. There's a point of time people don't do those things every day for them. Like it was, it's a gene tech. So a gene tech means basically it's an agent. It's meant to assist you. Um, Basically, you got agents and you get actuators, people that things that because you have to be determined. I prefer agentic. I prefer agentic model. Actuators. I said actuators, but I'm not gonna build actuators here. Actuators here, because those work as sensory dimensional sensory. I'm not. I'm gonna build robots that can perform to the degree I need them to perform for humanitarian aid. And that's the benchmark of progress to me. For progress to me. Thank you for watching this video. Thank you. Thank you. So I'm not building awareness systems. I'm building robotics interface systems. And I want someone to peer review my proof. So if you care enough, you can peer review my work. So just come in. Thank you for watching this video. If you come, you can peer review my work. You know, I've got it's on this repository here. I got it on my GitHub. GitHub.com for open patterns. But reach me directly on because I'm autistic, I'm on spectrum. This is going to reach directly on OKPALAN at proton dot protonmail.com. O for Oscar, K for Kilo, P for Papa, A for Alpha, L for Lima, A for Alpha, N for November at Proton, P for Papa, R for Romeo, O for Oscar, T for Tango, O for Oscar, N for November, mail, dot com. Thank you for watching this video.